That is that will go in on Monday. So if you don't, if you don't have it by Monday, you will see a 0 in there, and then you may get a call from your counselor immediately on that, because I believe our failures for this class are due Monday. So if you're right on the button right now and you get a 0 on this and it drops you down, and you didn't take the final, then that will automatically put you down below, and you'll get a call from your counselor until you send that in. If you do take the final and you pass it, then that excuses you from this assignment. You wouldn't have to take this. It still would affect your grade, is it still would go in as a 0. So if you're trying to do more than just pass the class, you would still have to submit this in. All right. So there we go with that. Let's take a look then at, oops, get down. There we go. Let's take a look at the final review. I think we can zoom better than that. Boom. All right, now Arrhenius acid. Arrhenius acids, we said acids start with H something something, and they increase the hydrogen ion concentration. Brackets mean concentration. We learned that with the weight laws. Hydrogen ion is an H plus there. Arrhenius base, what do these end in? OH, very good. So they usually have something something OH, and they increase the hydroxide ion concentration. What is it? Zoom it. Yep. Bronsted acid. Well, Bronsted and Lowry came along and said that, well, we can identify these a little bit different, because there are bases that do not have hydroxide in them, but they still act as bases. They still somehow increase the pH. So Bronsted acid is what we call a hydrogen ion donor, H plus ion donor. And that's an O. And a Bronsted-Lowry base is a hydrogen ion acceptor. So let's form common acid properties. One is they taste. How does acid taste? Like vinegar is an acid. How does it taste? Sour. Right? What's some other things with acids? They react with metals to form hydrogen gas. Well, actually, it's H2 gas. What else? Louder? pH is less than 7. That's a good one. pH is less than 7. Turn litmus paper red. That could be one. Feel watery. Right? 4 common properties of base. Soap is a base. How does soap taste? Like bitter. Yeah, right? They taste bitter. React with magnesium to form a precipitate. pH greater than 7. And they turn litmus blue. They also feel slippery, like soap. So it says a 0.001 molar nitric acid solution has a pH of 3. Is a solution acidic or basic? And that would be acidic. a 0.01 molar sodium hydroxide solution has a pH of 12. Well, that would be basic. List the names of the 6 strong acids. Well, we have HCl, H2SO4. So that's hydrochloric, sulfuric, perchloric. And then we have, including HCl, we have the other guys, hydrobromic and hydroiodic. HCl, yeah, brom, yep. And then the last one would be nitric acid. Remember, if it has no oxygen, you put hydro in front. So this is hydrochloric. If it ends in ATE, like sulfate here, you would put sulfuric or perchlorate, perchlorate. So you're going to need a periodic table with those polyatomic ions on them if you don't memorize them. Also, why does H2SO4 have 2 H's? Because the charge of sulfate is -2, so you need 2 hydrogens for that. List the names of the 5 strong bases. Well, this is going to be the alkali metal hydroxides, lithium, sodium, potassium, and cesium. And then one more with calcium hydroxide, an alkaline earth metal. We call Ca or Ma the molarity of a given concentration. For example, 0.25 moles per liter nitric acid, that is strong. So I'm going to call the molarity of that acid 0.25 molar. That means that the hydrogen ion concentration is equal to 0.25 moles per liter. What if I wanted to find the pH of this solution? Well, we would then take the negative log of that hydrogen ion concentration. That would have a pH of 0.60. So that's for strong acids. For weak acids, it's a little bit different. So perchloric, we said, is a strong acid. So 0.75, it will be 0.75. Again, if I want to find the pH of that, then I put negative log 0.75. Oops, extra point there. That would be 0.12 for the pH. Here we have a weak acid. So this acid is weak. So it has what we call a Ka of 0.00018. In order to find the hydrogen concentration of that, we take the Ka, which they give us, multiply it by the molarity, and then square root this. So 0.0018 multiplied by the molarity, 0.75, and then we square root that. That gives us the hydrogen ion concentration, 0.00018 times 0.75. Much different there. I'm going to go ahead and put that in scientific notation because it's long to write the other way. 1.35 times 10 to the -4th. So the fact that this is a weak acid means that even though these two concentrations are the same, it's going to have a lower amount of H3O plus. That's what determines how acidic something is. If we take a look, we have that concentration. We take the negative log of that. We find the pH of this to be almost 4, 3.87. So again, same concentration, but a weak acid. The Ka for this is even smaller by a factor of 10. So watch this. We do everything the same, 0.0004018 times 0.75. We square root that. We get 3.6 times 10 to the negative third. So then what we're going to do is we are going to square root. We already square rooted that answer. What we're going to do is we're going to take the negative log of that. And that will give us the pH. We get 2.43. Let me check one thing real quick. 0.00018 times 0.75. We take the square root of that. One, two, three. Trying to figure out why, yeah, I thought that may be wrong. 1.16, sorry about that. 1.16 times 10 to the negative second. Now let's refine the pH of that. Negative log answer. I must have accidentally hit something besides the answer. So we get 1.93 for the pH of this one. The pH, instead of the close to 4, it's 1.93. And then here, let's take the negative log of 3.67 times 10 to the negative third. And that's 2.44. The reason why I thought something was wrong there was because the pH of this one was going to be lower than the pH of this one if this were that 3.87. That couldn't happen because look at this Ka. This is a Ka that's greater. That means this acid right here is going to give up more of these H3O pluses than this one right here. The Ka determines the strength basically of a weak acid. The bigger the Ka, the stronger the acid. This is times 10 to the negative fourth. This is times 10 to the negative fifth. 10 to the negative fourth is bigger than 10 to the negative fifth. All right, same for bases. Again, I'm changing this M, that C to an M. So 0.75 moles per liter of potassium hydroxide means that we have a hydroxide ion concentration of 0.75. And remember, going around our four-corner diagram, we're going to take the negative log of that 0.75. But that isn't the pH. That's the pOH. So if we want the pH, we have to take 14 minus that. And that four-corner diagram allows us to get all of those different things. We take a look. Here's the four-corner diagram. We were up here. So we take the negative log to get the pOH. And then to get the pH, we take 14 minus that pOH. So 14 minus that gives us a pH of 13.88. Here we have a weak base. We know it's a weak base because we have those strong bases memorized. Or we can take a look and then see that give us Kb. So again, we're going to take the Kb, multiply it by that 0.75. So 1 times 10 to the negative fifth. I'm sorry, 1.8 times 10 to the negative fifth times 0.75. We need to square root that. That's going to give our concentration here, 3.67 times 10 to the negative third. So that's our hydroxide ion concentration. We take the negative log of that. That gives us the pOH. We're going to take 14 minus that to get the pH. We can see the pH for this weak base is closer to 7 versus the one for the strong base, which is closer to 14. If a solution is this much for the hydrogen ion concentration, what is its pH? Well, we simply take the negative log of 0.0045. Its pH is going to be 2.35. For a solution with a pOH of 2.41, what pH is, well, we take 14 minus 2.41. You basically have to go around that four-corner diagram to do these or have that memorized. So that is 11.59. Self-ionization of water. If we have two waters here, we can break that into H3O plus and OH negative. Basically, one water pulls a hydrogen off of the other water. Based on the above equation, we talked about the Kw is equal to 1 times 10 to the negative 14th. Or it looks like they want the value here, and they want the expression up top. I got a white out somewhere, I'm sure, here. So basically, Kw is equal to products divided by reactants, but since this is a liquid, we don't worry about it. So it's the concentration of H3O plus times the concentration of OH negative. A 0.25 molar HCl solution is 0.25 moles per liter of H3O plus. Use the K expression to calculate the OH negative. So that right there expression is the top line of the four-corner diagram. We have the hydrogen ion concentration. We want the hydroxide ion concentration. We take the Kw, 1 times 10 to the negative 14th. We divide it by that number. So 1 times 10 to the negative 14th divided by 0.25 equals hydroxide ion concentration, which equals 1 times 10 to the negative 14th divided by 0.25. We get 4 times 10 to the negative 14th. Moles per liter of hydroxide. Consider this. What is the Bronsted acid? So out of these two chemicals right here, which one is giving up an H? Which one is giving up an H out of those two chemicals there?
Isn't a NH2?
Well, NH2 is not giving up an H. NH3 is giving up an H to become NH.
HCl.
Yeah, there you go. And what is the conjugate base of that acid? So what did NH3 become? It became NH2. Don't forget that plus. And what are the two conjugate acid base pairs? Well, we know NH3 and NH2 plus, or 2 minus. Not plus, minus. Because it lost an H. There we go. H's are plus charged, and if you lose one, you become minus. If you gain one, you become plus. And the other two are CO3, 2 negative, gains an H, so it loses one of its minuses to become HCO3, negative 1. Take a look at 16. And I'm going to grab attendance real quick. I think that everybody should have had time to get in. Brianna, are you out there in the world? Nope. Cassie, make it into there. No Cassie. Gooch, nope. Come on, it's you. It's there. It's here. It's here. In November. All right, cool. So student uses 12.5 milliliters of a 0.5 molar HClO4 to titrate a 20 milliliter sample of the space. What is the molarity of the space? So we use MAVA equals MV. We need a balanced equation now. So we will take HClO4 plus CH3NH2. We're going to mix these two together and we're going to get ClO4 negative plus CH3NH3. And that balances out to a 1-to-1. So we're going to divide both of these by 1s. So we need to take the molarity of the acid times the volume of the acid, which is 0.5 times 12.5. This is just like a laboratory, 0.5 times 12.5. And then we're going to divide it by, we want the molarity of the base, so we divide it by the volume of the base, which is 20 milliliters. So the molarity of that base is 0.313. Oh, not OH, CH3 and H2. There we go. It says which one of these is monoprotic? Well, that would be this one right here, HC2H3O2. Since C2H3O2 is acetate, this would be called acetic acid, which is diprotic. This right here would be diprotic, H2C2O4. C2O4 is called oxalate. So this would be oxalic acid. Oxalic acid. And that means that this right here is triprotic, and this is arsenate, so that would be arsenic acid. Arsenate becomes arsenic acid. Boom. There you go. That's the review for it. Anybody have any other questions about the rest of the worksheet? The answers to this worksheet have been posted. They are on today's lessons. If you have no more questions, by all means, have a great day. I will see you guys, maybe next year.